My talk can be seen as a response from a mathematician's point of view to Philippe's talk. So I want to talk about seismology with a single seismometer, and of course there is a very practical reason why we would like to do that. And one thing I would like to emphasize here from the very beginning is that I'm talking about a mathematical theory, but notice the word towards. So I'm not claiming that we have a full and complete theory, and I don't believe we will have any in the near future, but we are building towards something in that direction. Okay, so let's get started. So I come from the University of Jyväskylä, which is located here in central Finland, and I'm part of the Finnish Center of Excellence in Inverse Problems, which tries to cover the entire map of Finland with inverse problems research groups. And one of the things the Finnish inverse problems community does is to organize an event every year. And the annual Inverse Problems Conference in Finland is called Inverse Days, and it will be organized in Jyväskylä this year. So the preliminary dates, which are still subject to change, are from December 16th to 18th. So anyone is welcome to come there. All kinds of inverse problems are welcome, so they can be numerical, applied, theoretical. It can be in differential geometry, it can be in geophysics, it can be planet exploration, just about anything. Okay, but then on to the actual show. So what I want to achieve here is that we want a reliable reconstruction of mass and backed up by theory. So we assume perfect measurements. So of course that's not going to be the reality, but to get started with the mathematical theory, we'd like to start at the ideal end of the spectrum. So assume perfect measurements from a single ideal seismometer. So maybe that ideal seismometer can measure things that InSight can't, but just in principle, what can you do with a perfect device? And the question is, what can you say for sure about the structure of the planet? And is there an inversion algorithm? So can you do something certainly and reliably from this data? So one objective is to identify useful data sets, and that can help future mission planning. Because of course, I assume that we'll be repeating this similar kind of idea on different celestial bodies in our solar system. And if we have a good theoretical understanding, we might know better what would be a good thing to measure and how there might be some mathematical insights. At least I hope so. So a grand goal is to have a mathematical theory of seismic planetary exploration. And that is a very grand goal, and I'm not going to give such a theory today. So my talk has two main parts. So one is to describe what we currently can do from the mathematical point of view on mass, and then the second part will be about what we can't do. And let's see. So let's get started with this Martian mantle. So as we know, and as Philippe explained in great detail, the InSight lander has deployed its seismic instrument SAIS on Mars in late 2018, and we want to figure out the structure of the planet from this data. And that is the outset. So of course there are various methods to fit a model to the data, and I believe physicists are usually better at developing these models than we are, these methods than we are. But the question is, how do we know that the obtained reconstruction is the only possible one? So do we have any proof of uniqueness that there is, that can we say for sure that there is nothing that we are inherently blind to? And is there maybe a way to reconstruct directly? So if you are given this data, is there a way to somehow directly compute from it instead of somehow fitting model parameters to match it? So a proposal, which is a naive mathematical one, is to start by doing reliably what can be done reliably with strong theoretical support. And there are some things that can be done in such a way, and I'll get to it in a minute. And don't guess or wave hands before you have to, but do so when you do have to. Because if I insisted that you can't do anything that I can't prove, then you can't really do much. But there are some things that I can prove, and it would be better if you got started with your physical problem by doing something reliable, and only then building on that towards something more elaborate. So for example, Mars is roughly spherically symmetric, not perfectly of course, but roughly as any major planet would be. And there are reliable ways to reconstruct a radial model of the mantle, or maybe just the upper mantle, from a single station. And this, if you reconstruct the mantle, that also means by implication that you know where the CMB, or the core mantle boundary, lies. Okay, so if you don't assume any kind of symmetry, you cannot expect to have a full 3D reconstruction from a single measurement point, but there's something you can do if you assume more. And I believe that this spherical symmetry is a good starting point. So I will ignore noise, all kind of model errors, finiteness of data, all kind of stability, and many other practical things. So it will be, unfortunately, unpractical at many levels, but I hope there is still something meaningful to the more applied people in the audience. So there are 3 methods that I'd like to describe to you. The first one is what I call linearized travel time tomography. So there are all kinds of noise on Mars, like on Earth, and they generate seismic waves, and they travel around the planet, they reflect on the surface and all the interfaces there are. And now, some of these waves are periodic, so it might go through the seismometer and it might come back after maybe 62 minutes, and again after 62 minutes, and then again. And if you calculate correlations in your data, you should be able to tell that there was a period of 62 minutes in the system. And moreover, if you can measure what kind of wave that was, or how was it polarized, what direction it was going, then you'd know the directions corresponding to these periodic travel times. So you know what kind of periodic things there are in the system, and you know some geometric information, but of course only at the single point where you can measure. Okay, so the data would consist of pairs. So there would be directions, so maybe angle from the normal direction, so the direction into the planet you are going to, and then travel times around the loop. And the unknown thing would be the wave speed, which I, as a geometer, tend to see as geometry. Okay, and I will come back to this geometrical point of view later on. Okay, and this will be useful in the second method, I believe. So the set of all these periodic travel times, if it's just an unlabeled set without any knowledge of the geometry, that is called the length spectrum. Maybe the periodic travel time spectrum would be more reasonable, but kind of geometrically, length spectrum is a good description of what happens. Okay, so that is kind of the data we would have. And let's see how we can reconstruct the geometry. So these wave speed variations can define a geometry, and the distance between any 2 points is the shortest wave travel time between them. So the time is measured in seconds, if you will, instead of meters. And now there are many kinds of geometries, so to say, because you have different polarization. You could ask for the QP distances or some quasi-SV distances or whatever you want. But I can just keep it at a general level here without worrying too much about polarization. Okay, so this geometry is conformally Euclidean if the material is isotropic. So that, you know, the geometry is kind of Euclidean, but there's a stretch factor that depends on the underlying point. So reconstructing the wave speed from travel time data is hard, usually. And even if you have data everywhere on the surface, there are results in this direction, but they are far from trivial, and they are far from applicable when you only have measurements at a single point on the boundary. So therefore, the solution is to linearize the thing, of course. Well, what else do you do when you can't solve a nonlinear problem? So the linearized data would consist now of a slightly different kind of information. So it would still consist of pairs. So there would be pairs of periodic broken rays, so kind of periodic things that go around the planet. I'll show you a picture in a moment. And then there are integrals over these curves. And those integrals are of a function, which is the unknown. So the variations of the wave speed are described by a function, and we know the integrals of that function. So this is some kind of an X-ray tomography problem. What you have is an unknown function, but you know some kinds of line integrals of your function, and you'd like to find what the function was. So here's a crude picture of Mars. So here's the core, here's the mantle, and inside is here. And here's one seismic wave that kind of goes from here and reflects on CMB, reflects on the surface and bounces back and forth, and it actually goes 3 times around the planet before making its way back to InSight. So this is one of the things that would be included in this data. So this length is included in the length spectrum as I defined. And also now what we had in the linearized problem is that we know the integrals over this kind of an unknown function over curves of this kind. Okay. So there is a theorem we proved with Martin. There seems to be a year missing, but anyhow, if the mantle satisfies the Hercule condition, which I'll mention in a moment, then these integrals over periodic broken rays determine a radial function uniquely. So if the wave speed is assumed to be radial, then this linearized problem will concern radial functions. So that makes life a little easier. So the Hercule condition is like this. So the wave speed, c, is assumed to be a function of radius only. And what you want is that this quotient, the radius divided by the wave speed, to have a strictly positive derivative everywhere. So it's probably valid down to some depth from the surface. And if that's so, then the results are valid up to that depth. So if the Hercule condition fails somewhere, we can still do the reconstruction up to that failure, or down to that failure, rather. And at least the upper mantle should satisfy the condition. The mantle of Earth will satisfy this condition, at least in PREM, for both P and S waves. So it's not unreasonable, but it's not entirely clear whether Mars should be geometrically as convenient as Earth. Okay, so when we solve a linearized problem, and we have a rather explicit way to do that, then that gives an iterative algorithm to solve the nonlinear one. So of course, you solve the linear one iteratively and hope you get closer and closer to your actual wave speed profile. So uniqueness should be provable for the nonlinear one as well, but that's not something we've been able to do yet. Okay, so that was one way to reconstruct the mantle from this data. And what I used here was correlations of the noise. So I didn't have to know what the noise is. I just know that there is sufficient amount of it, and I can do correlations and see these kind of periodic phenomena. The second thing is to use spectral data, so a different kind of thing. So like Earth, the Mars has free oscillation, so any planet is a drum. And the different kinds of events will play that drum, and we can listen to the frequencies. So these oscillations, just like the noise I mentioned before, they are excited by various things like Mars quakes, the atmosphere, meteorite impacts, and other possible events. And again, I don't really have to know what these events are as long as I know that kind of all the modes are excited to a sufficient extent. So these oscillations can be decomposed in a simple world that we mathematicians have into eigenmodes, which have their own frequencies, and these frequencies are precisely what make up the spectrum. So these different modes are excited differently in different events, so the amplitudes will vary in time. But one thing remains, and that is the set of frequencies. And that is the spectrum of free oscillation. So at first, I hope we are interested in the properties of the planet, not properties of the individual events. And then later, when we know what the planet is, we can go back to the data and see whether that data, whether it tells us something about the actual underlying events as well, when we have the framework to put it into. Okay, and the spectrum of free oscillations was chosen as one of these possible data sets because it's measurable from a single point. And that is, of course, important if you want to make a theory in the direction I want to. Okay, so mathematically, the spectrum of free oscillations corresponds roughly, so in a simple model, to the Neumann spectrum of the Laplace-Beltrami operator on a manifold. So if the sound speed is isotropic, so then the Riemannian metric tensor describing the geometry is given in this form, this Euclidean metric, which can be seen kind of as the identity matrix, and then just multiplied by the wave speed to power minus 2. So and that is kind of the simple model you'd expect. So in this geometry, the Laplace-Beltrami operator in n dimensions would look like this. So just to show that there is a kind of a simple enough formula which looks more or less like the elastic Laplace operator. And now we assume, of course, that wave speed is radial to keep things tractable. And again, wave speed is geometry. So here it's encoded in geometry, so the metric tensor in a very concrete way, just a conformal factor. Okay, so the question is, does the spectrum of free oscillations determine this wave speed profile globally, or how about just the mantle? So of course, when we just measure the set of frequencies, we cannot really tell how they are localized, but maybe we'll just first want to figure out something about the mantle. So for simplicity, I will assume that we measure the spectrum of the mantle, and the mantle satisfies the Hercott condition. So just to keep things simple, condition seems to be misspelled there, but anyway, neither assumption should really be necessary, but just for the sake of simplicity, I'll keep them in here. So the question is, simplified question is, so if a family of wave speeds, so wave speed depending on radius, but now depending on some parameter s, if that family has the same spectrum, then are all these profiles in the family the same? So that is the Martian mantle spectrally rigid, or kind of deformation spectrally rigid, if you will? So that is kind of a, well, somehow local or linear formulation of this question here. So here's a little theorem we had about this. So consider the annulus, that is the mantle, and mass is famously three-dimensional, so I'll play with 3 dimensions here. And I have a family of radial sound speed, which are smooth enough in both the parameter and the radius. And they satisfy some geometrical conditions. One of them is Herclots, and that is crucial. And then there is another one which I will actively ignore to mention. So if all of these if each one of these gives rise to the same spectrum, so of the corresponding Laplace-Beltrami operator, so the same spectrum of free oscillations, then all of these wave speeds actually have to be the same. So that is the simple model of the round Martian mantle is spectrally rigid. Okay, so the key observation behind this is what we call the trace formula. So suppose I have the eigenvalues, so these are kind of the measured quantities in the spectrum. Then I can define a function f like so as a formal infinite sum. And as you know, if you take an infinite sum of smooth functions, it may or may not actually define a smooth function everywhere. And now we assume that the geometry is nice enough. Then it so happens that the singularities of f, so the places where it fails to be smooth or continuous, are precisely at the length spectrum. So we call this the trace formula because this f is kind of formally the trace of the time derivative of the Green's function. Okay, so that is the spectrum determines the length spectrum, and therefore it suffices to prove this result for length spectral data instead of spectral data. And this the way this determination goes is rather weird. So you have these numbers, you plug them into a formula, compute a function, see where the singularities are, and the position of those singularities is what gives you the new data set. Okay, so here's a very simple example. So I have an interval from 0 to 1/2, and I have the Neumann first 5 Neumann eigenfunctions, which is fairly easy to solve, even I could do it. And the length spectrum is precisely the set of integer numbers, or maybe just the positive ones, depending on how you see it. So to go once around this periodically, you have to go from left to the right and back, and that makes unit length, and you can do that several times if you will. Okay, so that's a part of the spectrum. So from that set of eigenvalues I have here, I can compute the trace function, and lo and behold, there are singularities, so these kind of peaks are already starting to appear very clearly, and they are supposed to be precisely at the length spectrum, so the set of integers, and they are precisely at 1, 2, 3, 4, and so on. Okay, so it's a simple example to show that it will work, and now a more elaborate computation with Prem for the Earth shows that there is the trace will look messier because there's a whole lot of modes, and now it's since a numerical question how do you identify singularities and how do you decide what corresponds to what kind of mode and all that. But this trace function does contain information about the geometry, and that is kind of the main point I want to drive home here. Okay, so the theorem we had, so in order to prove the previous one, is that again I consider the same mantle and make the same assumptions, but now the claim is different. So if all of these different profiles in my family have the same length spectrum instead of the spectrum of free oscillations, then they all have to be the same. Okay, so the proof boils down to method A. So a radial function is determined by its integrals over periodic broken rays. So this can be reduced to the previous one, but the thing is that the data sets are still independent. So I think it would be useful to have different kind of data sets on which to base the same deduction, so to do it in a more reliable way, I hope. Okay, and then there will be meteorite impacts. So seismic events with known sources are of course a good source of information, and impacts are a nice choice. So we don't exactly know the form of the source, but we know that it will be sharply localized in space and time, as these hostile events tend to be. These make geometric methods more useful than PDE ones, typically. So if you make no assumptions on the that you don't know exactly what happens at the impact point. So an orbiter can of course verify the impact position, but the time will be unknown apart from rough windowing. So you know that something appeared on the surface between two consecutive pictures of the same region. Okay, so surface waves will come from the event. So just surface waves here at first. Two ways. So along the great circle containing the impact side and inside. So it will come the short way and the long way. So if there are no other events on the same great circle around the same time, so if these impacts are rare enough, then we can measure the time difference, and we also can measure the direction. And if you have multiple arrivals, so the same signal goes around the planet several times, then we actually know the time around the great circle as well. So that could be assumed to be known a priori. Okay, so here's a picture. So here's an impact. Here's the seismometer. And there will be two surface waves going both ways. Okay, so the two great circle distances, so the short one and the long one here, are easily solved from this data. So assuming we know the directions, then this means that we can deduce the place and time of the event. So this was all done on the surface, and now this gives rise to interior data. So of course there will also be body wave arrivals from the same event. And now, using those body waves, we can see now things within the mantle. So to get here, we only needed to assume spherical symmetry on the surface, but the arising problem is, okay, so we didn't need to assume symmetry on the inside, but of course it's easier to solve the eventual problem if you do assume the symmetry throughout the mantle. Okay. So here was the point, and using the surface waves, I could kind of calibrate the data so that I know when and where that impact was. And now then that gives me the body wave information that I know the travel time from this point to this point. And that is already very, very useful information. So this travel time information is enough to determine a radial wave speed, which is a century-old result. And the linearized problem is, again, kind of X-ray tomography, and it can also be solved explicitly, assuming radial symmetry. So to summarize these three methods, so we have three different methods to get a picture of the mantle, up down to the depth where the Hercules condition fails. It might fail somewhere mid-mantle. And this proves only work with one wave speed, but the results should still hold if you have full polarized waves, which is not something we've proved yet. And in the Earth, as I mentioned, the Hercules condition is actually satisfied in the whole mantle for both P and S. And on Mars, I hope it will actually at least hold in the upper mantle to get us started. And the three methods use completely different data sets. So if the reconstructions all work and give similar results, I think we should be fairly confident that this actually works out. And this gives us an isotropic radial symmetric reference model, so something similar to PREM, well, just fundamental, but still, which is a stepping stone then towards deeper and finer structures. Of course, this study wouldn't stop here, but this would be a good, reliable first step to a bigger picture of Mars. Okay, and here's all the data summarized in a single picture. So you have these periodic things which appear both directly and in the spectrum, and then we have these body waves which are kind of calibrated using surface waves. Yeah. So then, to take steps further, there are things that I'd like to see done. So whatever perturbation or iterative methods one uses, so when you step outside the realm of fully proven results, having a solid initial guess, of course, will help. And that is something we can do with rigor. And that is kind of the main message I want to give you. So there's a couple of things one could try from a mathematical point of view. So proving precise results is usually hard outside spherical symmetry. But you can linearize, so you can take perturbation theory and take these small perturbations in lateral directions and treat them with spectral perturbation theory, which is a well-established area. So that's something one can do. And so in a simple scalar model, the medium is described by a single wave speed, as before, and the spectrum is just a function of that profile. Then you can kind of write that. So if you again have a wave speed depending on the parameter, you can kind of linearize it. So there's the original spectrum, and there is a linear component, and you neglect the rest. And well, this plus is not an honest plus because those are sets, but anyhow, something in that direction will happen. And this Gateau derivative is something you can express quite explicitly. Okay, so solving this linear problem is essentially the whole thing if the deviation is small. So of course now this reference model would be the radial reference model that I kind of like almost got in the previous section of the talk, and then you could try to see which direction you should perturb that model to fit your data better, your spectral data better. Okay, so of course the better the radial guess, the better the perturbation theory will be. And that perturbation can be expanded in spherical harmonics, and the operator L can be written out fairly explicitly in terms of the spherical harmonics. So the question is, if we have a radial reference model that satisfies some nice conditions, then how uniquely does this linearized spectral data determine this perturbation of the wave speed? So there are a couple of observations at first. So there is a freedom to rotate, that's rather obvious. So if you rotate the whole thing, the spectrum will stay the same. But it also seems that we have these different spherical harmonic components, so that if you rotate all of them individually, it will still probably stay the same to first order. So there's a huge freedom of rotation, which is not kind of entirely the physical freedom you'd expect. And also, you can decompose that thing into symmetric and antisymmetric parts, and the antisymmetric part will play no role to first order. And it will have higher order contributions, but nothing in first order. Okay, and of course, we'd like to start with a scalar model in 2D and not a fully polarized 3D model. So we are kind of dragging behind with the actual demands of Mars, but that's the usual case with math. And one thing that kind of comes naturally is what I call half-local X-ray tomography. So if you recall the third method I had, so we assume that the surface is spherically symmetric or otherwise known and well-behaved, but we did not need to make any assumption on the interior. So this leads to a kind of travel time data. So the travel times, or geometrical distances, are known from all points on the surface to a single fixed point. So that is from all surface points of Mars, you know the travel time to the single seismometer that InSight has placed. Yeah, so you have a single fixed point and you are free, and so this stays put here, but now assuming that over time you have impacts everywhere on the planet, then you can measure these travel times from all points on the surface, ideally, to that single fixed point. So the question is, if I have a Riemannian or Finsler or what have you manifold with boundary, then is the metric uniquely determined by the distances between a fixed boundary point and all other boundary points? Probably not. This is very little data, but still this is the kind of questions that would naturally arise from this kind of data. And well, what if that point is replaced by a small open set? So instead of a single detector, you would have a small detector array, which of course it would be something nice to have, but of course a little harder to engineer and fund. So usually in the boundary distance rigidity problem, you have a manifold like my disk here, and you know the distance between all boundary points. So here I have 4 points in the boundary, and you would kind of know all these distances drawn here. But now I have an accessible region, so I have a measurement array. So of course I don't assume that the inside would cover 1/4 of the Martian area, but for the purposes of presentation. So now you would only measure. So the usual local boundary distance problem is formulated so that you only make measurements within your given subset. So you only know the distances between points in this small set here. And of course, because none of these curves actually goes into kind of deep into the manifold or into the planet, you can say nothing about it there. So you can only hope to reconstruct the geometry somewhere nearby. Okay, well, there are ways to do that. But now, what happens in this half local thing is that you have travel times, or these distances for these geodesics, but so that one of the endpoints is restricted to be here on this little set, but the other one is completely free to be anywhere. So this is kind of local only for the other endpoint. And now what one would like to do is reconstruct the whole thing, not just locally, but the whole thing from this kind of information. Okay, so the question that I'd like to pose here, which is just to hopefully get some mathematicians started. So let M be a manifold with boundary, and does this half local boundary distance data for any open subset U of the boundary determine the manifold uniquely? Assume anything you will about the manifold. If you just can prove anything in this direction, that would be wonderful. And of course, we can linearize the hard problem. So we take a manifold of this kind again. Now do the integrals of all these lines that I had in the previous picture, determine a function or a tensor field uniquely. So just know the integrals of a function over this kind of set of lines, and that can be seen as a partial data problem for X-ray tomography, which is rather well studied, but not with this specific question. So this is possible in Euclidean geometry, or if you have a real analytic unknown function or something, but it will always be unstable because you're missing a whole lot of directions deep in the planet, so it cannot be stable in any usual sense. Okay. So that was about the half local data, but then a couple of things about sources and receivers. So of course with InSat we only have one stationary receiver and we have no artificial sources, so we don't have any kind of controllable source on the surface or inside that we could use to send signals. So if we could have a small number of receivers and perhaps some artificial sources, what would be a nice way to place them? So would it be best to have them in a tight, small array somewhere locally, or should they be spread out around the planet? I don't know. But usually, if instead of one you had maybe 3 or 5 seismometers, you could maybe do much better. And it would be good to have some theoretical understanding as to why and how one should go about planning seismology with few stations instead of just one. And there's these things like freedom of rotation. So if you rotate the planet around an axis containing your single seismometer, some kinds of data will be invariant. But if you have several measurement points, you can usually kill these kinds of symmetric groups and maybe kind of make the kernel smaller and make the problem much more unique. So what is the minimal number of measurement points for uniqueness? And of course, this question makes no sense in isolation, but that would depend on the kind of problem or the kind of data set you pick. Okay, and well, I assumed the whole thing to be smooth within the mantle, so the wave speed doesn't jump abruptly. But of course, planets like Earth and Mars will have layers. And most geometrical inverse problems that we have in the literature now, they work with smooth manifolds. But what happens if you add conormal singularities? So instead of having a smooth thing all the way through, you'd have some jumps across some hypersurfaces, and maybe even a finite interior regularity. So between those jumps, maybe you only have C1 or C2 or C5 wave speeds or geometry instead of the usual C infinity thing. It would make a difference in physics, although geometers usually like to study smooth things. And of course, the question then is that how does spectral rigidity and X-ray tomography and all of that work in an onion when you have a spherical thing, or maybe not exactly spherical, and you have layered structure there? How does it all go through in that kind of setting? And one can also try to view things from a more geometrical point of view. So in many contexts, like measuring travel times or the spectrum, the measurements only see the wave speeds and nothing else. There are other physical parameters as well, but some of the measurements are only sensitive to wave speeds. And the speeds can be encoded as geometry, so the distance is measured in travel time, and geodesics in this geometry are the seismic rays. So they kind of go straight in this geometry. So what is the correct geometrical structure exactly to describe all of this? I have no answers there, but that's something that should be looked into in far more detail. And in a strongly anisotropic medium, as will be found inside the Earth, for example, the Riemannian geometry is not exactly enough, so you need something more, and it's some subclass of Finsler metrics that you end up studying if you allow for any kind of anisotropy. Okay, so once we recognize which physical quantities are relevant for the data, so for example, maybe only wave speeds, then we can focus on reconstructing what is visible and ignore the invisible. So that's the kind of theoretical understanding I was after. That if you can say that something will be completely hidden from us, then maybe try to kind of invert in a way that doesn't try to invert the invisible thing. And well, I mentioned these periodic things that will reflect on the boundary, and that is a natural thing with a single station. And there are a lot of hard questions here you need to get started with before asking your inverse questions. So maybe put any metric on the unit sphere and fix a point on it. So you fix inside on Mars. And how many directions are there so that the geodesics will make it back to the point, for example? Or how many periodic broken rays are there on a simple Riemannian manifold? I have no clue. But it's impossible to study the periodic broken ray transform if you don't know what the set of lines you are integrating over is in the first place. And maybe how does the X-ray tomography change when anosov flow is replaced by dispersing billiards? So anosov flow is something that is kind of a convenient open set of geometries on a manifold that allows for a nice study of X-ray tomography. And maybe if you want to bring that same study to now these things with surfaces, then dispersing billiards would be kind of the correct way to go. But then again, I'm not sure how to make all of this theory work there. So there's a lot to be done. So I hope these problems that I gave, so both the solved ones and the unsolved ones, I hope these are relevant for physicists so that you see these as something that are not just an exercise that you can safely ignore. And hopefully also interesting enough for mathematicians to something to actually look into in some detail and see whether something more could be done. So we do not have a complete geometrical theory of elasticity, so the geometrical picture is rather incomplete. Nor do we have a mathematical theory of seismic planetary exploration, but certainly we're taking steps towards both of them, so we don't have this yet, but I hope someday in the future we will, and I hope some of you will be involved in this journey. Thank you.